Hallo, it's dumplet here. Here's an item on geometry. In the figure, we do have a red semicircle and the segments and the points as indicated in the figure. These two angles highlighted in blue are of the same measure. Find the length of AE. Oh, by the way, O is the center of the semicircle. Credits to the Philippine Mathematical Olympiad for this item. As usual, pause this video if you'd like to give this item a try. But if you're done, let us dive into the solution. Okay, so here we have a geometry question. Now, I think one of the primary observations would be that we would be able to use the power of a point. Now, we want to find AE, and it's pretty nice that AE is involved in the power of a point here because AC and AB are secants. Now, by the power of a point, we should have AE times AC, and that's going to be equal to AD times AB. Now, AD is 9, and then AB, the entire thing is 9 plus 4, which is 13. So we do know that AE times AC is 9 times 13. So before we can know what AE is, we have to kind of know what AC is first. Now, take a look at AC, and we try to see, well, how can we deal with AC? Now, because of the properties of the circle over here, we should be able to kind of move our attention, switch our attention to finding AC. Now, we do have a semicircle here, and it's technically half of a circle. And well, since it's a semicircle, the CB over here, that's going to be a diameter. So we would be able to obviously see here that this angle must be right? This must be a right angle since it's technically the inscribed angle here of a semicircle, right? So by the Taylor's theorem, angle CDB should be right. Next, we could try to see to use the angle conditions. Well, both of them are equal to, let's just say, alpha for now. And well, arc DB over here is intercepted by this inscribed angle DCB. So it's going to be half of this one, which we know it's going to be of alpha as well because the central angle is alpha. So divide alpha by 2, and that's going to be the green angle over here. Now, just because there are fractions over here, I just kind of want to get rid of fractions. So let's just keep our calculation simple. I'm just going to say that this part in the middle, let's just say it's x, and that's going to give 2x to this and this one, the two blue angles. At least no fractions involved. Now, we do have two right triangles in effect because we do have a right angle here at point D. So that's going to be our next target. Now, our two triangles of concern are triangle ACD and triangle CBD. So let's try to figure out something first because there is one unknown length of CD. But we do know that CD is part of the two triangles. Now, it is also worth noting that in triangle ACD, we do have this 2x angle, and in triangle CBD, we do have this x angle. So, kind of expected, we might have to do some identities, double angle identities, because of the given angle conditions. So, in triangle ACD, well, I can try to get some trigonometric ratios here, but the relationship between two triangles, they're kind of connected by a common denominator here of CD. So CD is a common segment to both. So maybe I want to involve CD. Now, if I want to involve CD, that's going to mean that taking the tangent of 2x would be beneficial. So if I try to take the tangent of 2x in triangle ACD, so tangent of 2x, that's going to be equal to 9 divided by CD. Okay? That's going to be 9 divided by CD. And in triangle CBD, I want to involve CD, and well, there's this given of 4, so I guess the tangent as well. So the tangent of the x, so here tangent of x in triangle CBD, I can write it as 4 over CD. Now, this is technically a system of equations in two, I'm going to say, variables, CD and tangent x. Because we can express tangent 2x using the double angle identity as twice tangent x divided by 1 minus the square of tangent x. That's going to be the expression. That's going to be the identity, the double angle identity for tangent. And then remains the same, 9 divided by CD. And I could use these two, this and that, to help me get a CD and tangent x. So, but I think it's easier to get tangent x. So I'm going to divide the two equations. I'm going to divide the first one by the second one over here. So if I divide the first equation by the second equation, I will get the following. I'll get that 2 divided by 1 minus tangent squared x. That's going to be equal to 9 over 4. Okay, 9 over 4. Now let's do some cross multiplication. I'll get 8 is equal to 9 minus 9 tangent squared x. Okay, moving on from here, I'll get that 9 tangent squared x is equal to 1. Okay, so I'll get the tangent of x is equal to 1/9. Tangent squared of x is 1/9. So tangent x would have to be plus minus 1/3. Now, but based on the figure, x is going to be acute. And we can actually prove it's going to be acute because the figure might not be drawn to scale. But take a look at angle x. Angle x is an angle in a right triangle CBD. So CBD over here is a right triangle. X is not the right angle, so x must be acute. Okay, so we can guarantee that x must be acute. So tangent of an acute angle must be positive. So we're only going to have 1/3 over here. Okay, now having tangent x to be 1/3, technically I could substitute it into here to get CD. So tangent x is equal to 1/3 as acquired. So 4 is to CD is 1 is to 3. And that's going to obviously give me that CD is going to be equal to 12. So this part would be of length 12, right? We're going to highlight this, right? That's going to be of length 12. And that's pretty good because recall the power of a point that we want. We could kind of get AC before we get AE. And in our case, we could get AC now actually because we're going to refer back to triangle ACD. Well, it's a right triangle and we do have the measure of 2 of its legs, the 9 and the 12, which is pretty nice because I would know that AC would have to be the square root of 9 squared plus 12 squared. Actually, a very famous Pythagorean triple, 9, 12, 15 in the ratio 3 is to 4 is to 5. So we're going to get that AC is going to be 15. And that's going to be the last piece to our puzzle. We have AE times AC, which we now know it's 15. So AE times 15, that's going to be 9 times 13. We divide both sides by 15. AE would be 9 times 13 divided by 15. We could cancel the 9 and the 15, 3 and 5. So AE would be 3 times 13, that's 39. And then the denominator is just as it is, so 5. So the length of AE, as required in the problem, is 39 over 5. And this will be our final answer. Hopefully you guys learned something new from this video, and I'll see you in the next one. Bye-bye.